All right, so the first one we're going to dig into is the notion of storage optimization. And here, what I'm really talking about is, the same data in our tables, but just consuming less space. And that consumption of less space has implications for both your storage costs. So literally, at Netflix, we were all using AWS services. And so for our Iceberg tables, or our data lake, that was S3. And so if you can have the same amount of data in a smaller S3 footprint, that translates directly into cost savings. And at Netflix scale, that was millions of dollars of S3 savings per year. But it also translates into savings on the compute side, because the reality is, if you have less data and you're writing queries against what is less data on disk, then your compute performance improves and you need less computing resources to process the same queries. And so you get wins both on the storage side and on the compute side when you're able to reduce the footprint of your data warehouse and your data lake. And the way to do that really is what I call the 4 C's of storage optimization. And we'll go into these a little bit more. So the first one is columnar, right? This one should be relatively obvious. It isn't necessarily an Iceberg feature, but certainly Iceberg supports and has great support for leveraging columnar file formats. In fact, it doesn't support using text formats like JSON or CSV. You have to use Parquet or ORC within an Iceberg table. And they just, compress and store a lot better than, the text-based storage format like JSON. The second one is compaction. Compaction is the process of taking lots of small files that are potentially produced by streaming applications or by ETL processes, or through other modes of ingesting data into your lake and your data warehouse. And you want to combine these together. And that does two important things for optimization here. The first one is really improves your compute performance, right? If you have to read 10 files instead of reading 1,000 files, that's just going to be much more performant in these distributed systems like Spark, like Trino, Athena, Snowflake. Any of these systems are going to run better on having to process less files. And the other thing is that when we start talking about these other C's, compression and clustering, they're also improved when we put these small files together. You can imagine, if we're using advanced compression techniques, the more similar data we can put together into a single file, the more those compression techniques actually will remove redundant bytes from the underlying data storage. So compaction has a win on a couple of fronts there. The next one is compression. And this one actually is probably the one that folks pay the least attention to, but is actually an easy win. And it's pretty common that I've seen that people are just going to use whatever the default is in, say, like Spark or Trino in terms of compression. That may be Snappy is often a default compression codec that gets used. Maybe it's gzip. Maybe it's standard. But the reality is, for any given data set, the best compression codec to choose varies. And so to really do this correctly, what you need to do is actually run experiments on your production data. You want to basically try all these different formats on your real data and see which ones have the best trade-offs in terms of both size and performance, right? Because you can highly compress data and maybe save on storage space, but then you waste a lot of CPU cycles, both reading and writing that highly compressed data. So what you want to do is find that happy medium balance point where you're getting the best compression in terms of reduced storage, but also great performance in terms of the CPU cycles on the read and write side for that stuff. And that can be a tricky one, but there's big opportunities for wins there. And then the last one is around clustering. And this is, just keeping similar data co-located. Again, this has benefits for certainly on the query side, right? If you keep data together that you're often, say, filtering or using predicates against in your queries, that's going to allow you, the query engines, especially if you're using something like Iceberg, to really use all the Iceberg metadata and indexing to prune away files that aren't necessary for the query, and you're just going to have to read less data. That's a massive win when it comes to compute performance and cost savings, related cost savings. But even beyond just the query performance and savings there, again, when you are clustering data together, your compression and your compaction will work even better. So there's just physical storage improvements you get from choosing the ideal clustering keys. And again, this is usually done through experimentation. You have to try different clustering keys and different sort orders to find the balance between both storage optimization as well as query performance. Right, so the first two are relatively easy. Using columnar formats, making sure you're compacting, but picking the right compression codecs, picking the right clustering algorithms, that is more complicated. And that's really where Apache Iceberg and Tabular come together to give you some real power. So the first thing that Iceberg allows us to do across these 4 C's is make these configurations declarative. So in a non-Iceberg world, like say at Netflix, when we were using primarily Hive tables, getting all this information in terms of making sure we had the right file sizes, making sure we had the right compression codecs, making sure that we were sorting the data correctly, all of that logic had to be written by data engineers and plugged into whatever the jobs were that were writing the data. So if you were doing Spark ETL or you're doing a stream processing job, you had to understand what the desired outcome was, and then you had to make sure that you programmatically added that information to your, say, Spark job in order to get the output that you wanted. And Iceberg really turns that problem on its head, and it says, hey, let's just make this declarative. Let's set what the target we want is in the table, and as part of the table metadata, the table properties, and then let that drive how the engines behave and how the engines write out data. And this is a much more powerful mechanism because it doesn't require the data engineer to necessarily have to go through every single job and get the settings correct. We can do this at a platform level. We can do this programmatically. We can do it in an automated fashion, and that turns a lot of power back over to the platform. The other thing that Iceberg allows us to do, because Iceberg enables multiple different writers to the same underlying table, right? And giving us these ACID guarantees that we didn't have in Hive-like systems, we can have deferred work. So in a streaming application, it's sometimes not very desired to do a bunch of this like sorting and clustering and write larger files, because in a streaming application, you really care about your throughput, and doing that extra shuffling can really back up your stream processing. So what you want to do is let the stream write out data potentially in a non-optimal format, but have background processes that go through, use the Iceberg configuration properties, and rewrite data into a better shape for downstream, batch query consumption. So you can have, different styles of, write throughput as opposed to like batch query optimization on the other side by using this deferred work concept. So this is a powerful thing, something we leveraged heavily at Netflix in order to really automate getting optimal settings across our entire warehouse. And again, millions of dollars in just S3 cost alone, and Spark and Trino and other queries. So what does this actually look like in Iceberg? We can use table properties like our ordering, partitioning, as well as parquet settings. All of these become declarative at the table level, so we don't have to add this information into our ETL jobs. We declare at the table level, and the ETL jobs will automatically respond to that. And in particular, like in this bold thing here, what it does is unlock the automatic optimization. So once you've moved the problem from being a data engineering problem to being a data platform problem, now you can solve it centrally and you can automate it. And that's where Tabular comes in. So part of the Tabular, value proposition is a platform that automatically handles, implementing the 4 C's for your data warehouse. It does compaction. It does compaction intelligently. It watches for commits and changes to your Iceberg tables, and it decides when is the right time to compact. It waits, to have enough small files that can get the target file sizes it wants. It understands what kinds of compression it's going to get on that, It does those experiments. I mentioned like running experiments to figure out what is the optimal balance in terms of size and performance. Our system behind the scenes runs a bunch of these little experiments on data to figure out what is the optimal compression codec. It then sets those things in the table and uses them during compaction processes to make sure your storage is always in an optimal state. It also figures out what are the best fields to be partitioning on, to be sorting on, again, to balance storage performance as well as query. And the end result of all that is that Tabular customers on average see a reduced storage footprint of 40%. So a very significant reduction in just bytes on disk. For the same exact data, we've reduced the size on disk by 40%. That's hard cost savings, say for like your object store, and also query performance improves and query costs go down across all your engines. So this isn't engine specific, right? This is engine agnostic. It's done at the storage layer. So whether you're using Spark or Trino or Athena or Snowflake or whatever engine you're using, you're going to see those benefits. So that's a sort of a very powerful thing that Iceberg unlocks and Tabular really takes advantage of.